Hello, so in this video, we're going to talk about something which we've talked about before, albeit very briefly, and we will talk about again. And it's this thing called linear dependence and the Wronskian, okay? And I'm going to kind of hopefully build the picture up in your head and talk a little bit more about why the Wronskian is so important, and hopefully actually introduce a new theorem as well, which is kind of related to all this. Okay, so first of all, I'm going to talk about this idea of linear dependence. Now, you know, if a child is dependent on its mother, okay? Dependent. So I want to talk about this idea of linear dependency, but it's very much related to the kind of dependency, the word dependency in the everyday sense of the word, okay? So dependence, if a child is dependent on its mother, it means it relies on its mother to work, or it relies on its mother to function and to live and things like that. So, yeah, and the similar kind of thing with linear dependency, except it's linear because it's kind of, you know, linear stuff is basically it's not raised to any power, it's multiplied by any other function or anything like that. So it's linear, so it's simple, keeping it simple. And if it's linear dependent, then basically what that means is that one function, solution, variable, okay, depends on the other variable in order to work, in order to write it, okay? So for example, if I have two solutions, I don't know whether I've shown you these before, but y1 equals e to the 3t. So that's one solution. Say if we have a second order differential equation, okay, and we get one of the solutions out as e to the 3t. And let's say that the other solution is 2e to the 3t. Okay, well, it doesn't take a rocket scientist to work out that, you know, y2 is just simply dependent on y1, because look, this e to the 3t is this y1. So in other words, we can say that y2 is just two lots of y1. So in other words, y2 and y1 rely on each other to depend, you know, y2 depends on y1. Or equally, I could write it, I suppose, as y1 equals a half y2. That's fine. But basically, the idea is that because one solution could be written in terms of the other solution, okay, like I've got there, you know, one solution is a multiple of the other solution, then therefore it depends on it. They depend on each other. They've got that relationship. It's like a mother and child relationship. Okay, they depend on each other to work. Okay, and so yeah, basically what it means is that one solution can be written in terms of the other solution, or one is a multiple of the other. Okay, and obviously the opposite of that is independent, so linear independence. So independence, I think no, I haven't spelled that right. There we go, independence. So if it's independent, it's obviously the opposite of that. You know, as you grow older, you grow out of relying on your parents, or a child grows out of relying on its mother. Okay, and so when we compare that to solutions, it basically means the opposite case, that, you know, one solution cannot be written in terms of the other solution. Okay, so if you get dependency in your head, then it's pretty easy to work out what independence is, because it's just the opposite case. Okay, and we also, another word for independence is fundamental, because it basically means that we can't break, you know, if it's fundamental, it means we can't break anything down any further. Okay, if something is fundamental, it means it cannot be broken down into smaller parts, right? Well, fairly obviously, these solutions which I've written down here are not fundamental, because, you know, y2 can be broken down. If I just, there you go. So y2 can be broken down into elements of y1. Okay, so therefore they're not fundamental. Fundamental means they can't be broken down any further. Well, if it's dependent, it can be broken down further. Whereas if it's independent, one solution is not written in terms of the other solution, so therefore they cannot be broken down any further. Okay, so this is kind of the idea in your head, which you know I've introduced before, behind linear dependency and linear independency. But there is also another way that we can define it. It's exactly the same thing. It's just saying, you know, it's the same definition before. You know, it's the same definition as this. It's exactly the same thing what I'm about to present. It's just in a different way. It's just in a different form. Okay, so we can also say that linear dependency, okay, satisfies this. So for certain constants, c1, y1, plus c2, y2. So in other words, we write these two solutions, y1 and y2. We write y1 and y2 as a linear combination. Remember, I've talked about linear combination before. Yeah, you just take y1 and y2, you add them together, and then you can have any multiple of those two solutions there. Okay, and that's kind of a nice, neat way of combining two solutions together into one. Okay, and basically if we set this equal to 0, then there exists some c1 and some c2 such that this is satisfied. Okay, and they can't be 0. At least not both of them can't be 0. So one of them could be 0, but we just generally say that they can't be 0. That neither of them can be 0. So basically either C1 can't be 0 or C2 can't be 0. Basically, what this is saying is that one of there are constants that exist. I don't know what those constants are, but there are constants that exist that make this the case. Okay, well, fairly obviously, this is just the same idea as this, just presented in a different way. Because look, if I just rearrange, this, hang on. Okay, so let's present it like this. Getting a bit messy before, so let's just present it slightly neater. So in other words, if I just rearrange this thing, so I end up with C1y1 is equal to minus C2y2. So remember, just C1 and C2 are just numbers, okay? Then therefore I can say that y1 is just some multiple, so C1, C2 over C1 now, times y2. So therefore I can say that y1 is just some multiple of C2. If I just write this are just, this is just going to be negative, this is just going to be some number, right? Because it's C2 over C1, they're numbers, so therefore that's going to be a fraction, so it's just going to be another number. Then take the negative of it, that's still going to be another number. So if I just rewrite that as C3, say, it's just another constant, or even just K. Yeah, if I just write that as K, so in other words, one is a multiple of the other number. That's exactly the same as what I've got there. It's exactly the same as what I've got there. So if you wanted to just if you wanted to use this example, say, to see if it satisfies that, which it should do, because I've shown that they're linear dependent, by this. So let's have a look. So we've got C1y1 plus C2y2 equals 0. So let's just replace y1 with e to the 3t and with y2 with 2 e to the 3t. Okay, then basically let's just have a look at this. So we've got this plus this. So therefore let's just do a little bit of rearranging. So C1 e to the 3t. So actually no, let's just divide through by e to the 3t. Of course, that's the obvious thing to do. Let's divide through by e to the 3t. So we end up with C1. So let's just rearrange this. So we end up with C1 equals minus 2C2. Minus 2C2. Okay, well then obviously because C1 equals minus 2C2, then some. Basically, what this is saying is that I can just replace C2. So where are we? Let's put E32 back in here. So if I just replace C1 with minus 2 C2, then basically I can rearrange this to get what do I end up with? So minus 2C2 plus C2, so plus 2C2. Plus 2C2, if I write it around like that way. So minus 2C2 plus 2C2 equals 0, which of course it does. They both cancel out. So therefore I've found, constant. There does exist some constants, such as that is the case, okay? And C2 doesn't have to be 0. So in other words, I've found a solution where that is the case, okay? So therefore that's linear dependence. So that's exactly the same idea, just presented in a different way. Okay, whereas linear independence, remember, linear independent just means that, that they can't be written like this. One can't be written as a constant times another constant, so not multiples of each other. So therefore, what does that mean? Well, I'm not going to go through it now, but I'm not going to go through it in such detail. But basically, if you want to write C1y1 plus C2y2, so exactly the same linear combination before, and set it equal to 0, if you want this, then the only possible option is if both constants are 0. That's the only possible option. Okay, if they're linear dependent, you choose your constants such that they're not 0. Okay, but here, if they are linear independent, then therefore the only possible option you can choose is if the constants are 0, if both are 0. Okay, so in other words, no k exists. So therefore, y1 is not a multiple of y2. So therefore, the only option that you can have is if the multiple, which you want to find the multiple, which is k, which is just going to be a function of c1 and c2. Remember, k was just, what was it, minus c2 over c1. Yeah, so the only possible option of c2 and c1, because, k you want to be 0, the only possible option for that is to have 0 over 0, or, get them equal to 0 effectively. Okay, so yeah, that's kind of the idea behind that, because k must be equal to 0. So do you want to see an example? Okay then. So let's try and verify whether these two solutions, okay, so you've got y1 is some solution to, let's say we've got a different, a second order differential equation, get these two solutions out, and you want to verify whether they are in fact whether you want to verify whether or not they're dependent or linearly independent. So let's have a look. So basically the idea is you want to set up a linear combination, so c1y1 plus c2y2 equals 0, and you want to basically verify, well, what are the choices of the constants? What are the choices of the constants? What choices of the constants do we have to make? And if they're both equal to 0, then it's linear. So remember, if they're both equal to 0, then it's linearly independent. Whereas if not both of them are 0, so c1 and c2 not equal to 0, then therefore it's linearly dependent. It's dependent. Okay, so that's basically what we want to find. We want to find the constant such that this satisfies. So okay, let's just sub it in. So we end up with c1y1, so c1 lots of sine 2x, okay, plus c2y2, so c2 lots of sine x cos x equals 0. Okay, well, let's try and rearrange this just for a minute. So let's end up with c1 sine 2x. c1 sine 2x is equal to minus c2 sine x cos x. Okay. Do you know your double angle formulas? Because there's a double angle formula which goes like this. Sine 2x. So sine, well, maybe if I change it to a then. So sine 2a is equal to 2 sine a cos a. Okay, just from your double angle formulas. I mean, the thing is, I look at this and I've kind of been doing them enough, although I don't necessarily know them off the top of my head always. I have to kind of think through a process to get to them. I know they exist, and I think that's far more important. Knowing that a formula exists that you could use is far more important than actually knowing the formula by heart. Well, I mean, if you know the formula by heart, that's obviously better. But I mean, sometimes it's so important. It's more important to actually know that a formula exists, because then at least you can go away and look it up. So that should be ringing bells. So therefore, if you just compare these two, okay, well, we want basically this thing to look like this. Okay, well, we can make c1 1. So if we make c1 1, then we get sine 2x. So c1 equals 1. We end up with sine 2x, and we want 2 sine x cos x on the right hand side. Okay, we want 2 sine x cos x on the right hand side. So in other words, we want minus c2. So we want c1 equals 1. That gets that. Okay, but we want a 2 here. Well, in order to make 2 here, we want minus c2 equals 2. So therefore c2 must equal minus 2. So those are your two solutions. They're not both 0. Okay, they're not both 0, so therefore we can say that y1 and y2, so we've got this situation going on. Therefore, because c1 and c2, we've found out that c1 and c2 are not both 0, okay, so therefore y1 and y2 are linearly dependent solutions. So in other words, one of them relies on the other one. So in other words, one of them relies on the other one in order to be written, okay? So you may be saying, well, okay, fine, I get linearly dependent and linearly independent solution. I kind of get the idea now. Okay, thanks, Alex. I get the idea now. But why would I want to do that? Well, remember, I come back to this idea. So we've got y1 and y2. These are two solutions. However many solutions you've got, y1 and y2. Okay, let's deal with the two-dimensional case at the moment. So y1 and y2 are your two solutions. And you want to see whether they're linearly dependent or independent. Why? Well, if they're linearly dependent or linearly independent, let's choose. So if they're linearly independent, that basically means that they're fundamental. They're fundamental. So one cannot be broken down into elements of the other. Okay, so they can't be broken down any further. And of course, fundamental solutions, as you'll come on to see, or as you'll come on to see with things like systems, okay, and you may have already seen with a couple of videos in the past, that fundamental solutions are really important, because then we can form things like fundamental matrices, okay, and we can essentially, if you don't really want a solution that's consisting of other parts. If you can kind of get to the heart of it, if you can get to the core of things, then that is obviously, that's often far more useful. Okay, so basically you want to tell whether they're linearly independent or linearly dependent. Okay. Okay, so basically, how do you tell whether they're linearly dependent or linearly independent? Well, a quick way to tell is by this use of the Wronskian. So remember the Wronskian, maybe if I just pull this down. So remember the Wronskian, we've defined, the Wronskian of two solutions, y1 and y2. You can have as many solutions as you like, but it needs to form a square matrix. So this tells you how many derivatives you have to take of, let's say, some particular value, let's say t0. Well, that's given by y1 evaluated at t0. And y2 evaluated at t0, okay? But you want to make this a square matrix, because eventually you want to end up taking the determinant of it. And of course, you can only take the determinant of a square matrix. So you've got two columns, therefore you need two rows. And in order to get that second row, you can take the derivative. Okay, you end up with a solution that's related. You end up with something that's related to your top row. You need something that's related to your top row. Well, the derivative seems like a pretty good place to go, because obviously a derivative, the word derive, it comes from, so they're physically sort of related, like father and son, I suppose, if you want to use a family analogy. So that's what the Wronskian is. Okay, now if you remember that, I kind of showed you very briefly, I think, in one of the last videos, that if they're linearly dependent, then basically the Wronskian is 0, so linearly dependent, the Wronskian is 0, and if they're linearly independent, the Wronskian's not equal to 0. Okay, and essentially that's because there's a cancelling out process that occurs in the determinant. So let me try and show you. So let's have a look. So let's choose the two things that we had before. So y1 equals e to the 3t, the two solutions we had before. So y2 equals e to the 2 e to the 3t. So these are the two solutions that we have before. Okay, two solutions that we have before. And we know they're linearly dependent. So in other words, we expect that the determinant of the Wronskian is going to be 0. So let's make the Wronskian up. So the Wronskian, let's choose the initial condition. I don't know. Well, actually, let's just go with it. So the Wronskian will be e to the 3t here, and y2 is 2 e to the 3t, 2 e to the 3t. Okay, and then in this row we need the derivatives of them. So derivative of e to the 3t is 3 e to the 3t. Okay, and the derivative of 2 e to the 3t is 6 e to the 3t. Okay, so let's have a look. And of course, I've defined the Wronskian as just we put in a particular value. But actually what you're later going to come on and find, or what we're going to find in just a moment, is that actually you can put in any value for the Wronskian. So in other words, you can put in any value for the Wronskian and it will still work. You can put in any value for the Wronskian and it will still work. So actually I'm just going to go straight ahead because, I know this new fact. And you can see that actually because as cancellation occurs, it doesn't matter what value you put in. It should come out. So we end up with e to the 3t times 6 e to the 3t minus the other diagonal. So 2 e to the 3t times 3 e to the 3t. Okay, so what do we end up with? So let's have a look. So we should expect these to be linear dependent. So in other words, it should be cancellation. So we end up with 6 e to the 3t. No, we don't. We end up with 6 e to the 3t times e to the 3t minus 6 e to the 3t e to the 3t. Okay, well, hopefully you can see that they're the same. You can do as next step to cancel off, but you can see that they're the same. They immediately cancel off, so therefore that should be 0. So therefore we verified they are linearly dependent from the Wronskian. Okay, and obviously if they're so essentially because a cancellation occurs, then that's why the Wronskian should be 0, because one should be a multiple of the other. So therefore, when we take the Wronskian, then there should be a cancellation.